Okay, so this theorem is just covering some of the basic properties that linear transformations have. Proving them is very, very straightforward. Your book proves part A. I'm going to prove part B to give you a different proof. And then, the proof of part C is going to follow very similar steps. So basically what we're saying here is that if T is a linear transformation that maps V into W, then you have these three properties. First of all, T of 0 equals 0. Again, pay attention to where the zeros here live. These are not the same zero. They look the same. But if I wanted to be really specific, I could have put subscripts on this: 0 sub v, 0 sub w. Remember, this 0 is being plugged into the function, which means it's the 0 vector of v. This 0 just came out of the function, making it the 0 vector of w. And as we've shown, the 0 vector here is not necessarily the same thing as the 0 vector here. So make sure you know where these things live. These are not necessarily the same. T of u minus v satisfies a property similar to the additive property. It's equal to t u minus t of v for any vectors u and v in the vector space v. Also, you can pull negatives out of t. This one's, we're not proving this here, but it's super easy to prove. Remember, this is just going to follow from homogeneity. Negative v, it turns out, is the same thing as the scalar -1 times v, and we know that scalars can be brought out of linear transformations. That's all that's happening there. Let's just prove part B really quick. So let's let T be a vector space mapping V into W, or a linear transformation. Should say linear here. A linear transformation mapping V into W. Let U and V be any vectors in V. Then if I were to try and evaluate T of U minus V, I know that this is the same thing as U plus -1 times V. We've used this method for thinking of subtraction in terms of addition many times in the past. Now, because I've changed this into addition, I get to use the additive property that linear transformations have. I can split this into a sum of T of U plus T of -1V. This -1 is a scalar, which, because T is a linear transformation, we know it can be brought out by that homogeneity property. That's what's happening from here to here. But -1 times T of V, remember T of V is a vector that lives in W. -1 times T of V is just the same thing, if I'm adding that, as T of U minus T of V. That establishes that theorem. It's very direct, very straightforward proof, just using the basic properties of linear transformations. All right. So let's talk about some non-examples. What kinds of transformations are not linear? So this one, your book talks about this one as well. This is going to be the linear transformation that takes square matrices from the space M and N, so n by n matrices for some value of n, into the real numbers, the vector space R, and it's going to be defined by the function that takes the determinant of A. Notice the input would be an n by n matrix. The output is going to be a scalar, because that's what determinants do. Now, to show that this is not linear, we use a property of determinants. This is the way your book approaches it, and it's really kind of the most natural way. So we want to show that this vector space fails one of the defining properties. If I say let A be a vector in M and N, and K, and I need to be specific here that K is not equal to 0. We'll see why in a second. K not equal to 0 is, let that be a scalar. Okay? Then, what I'm going to do is show that homogeneity fails. So homogeneity would say, start by looking at T of Ka. Well, by definition, this is the determinant of Ka. Now, we have a property for determinants that says that if you take the determinant of Ka, this is actually the same thing as k to the nth power. Remember, what you can do is pull a k out of each row of A. And because there's n rows of A, we end up with n k's being multiplied out here. That's equal to the determinant of A. In fact, I'm going to add one more little condition here. I'm going to say k is not equal to plus or minus 1. it can be, the scalars are real numbers, so we have choices of k that are not equal to these values. Then this is definitely not equal to k times the determinant of a. Here's where I need this this assumption here. If k is equal to 0 or 1, then k to the n is equal to 0 or 1 respectively. So this would in fact equal this in the case where 0 is equal to, k is 0 or 1. The reason I'm also ruling out k equals -1 is because if n is an even number, then k to the n would also equal k in that case. But any other case, if k is equal to something other than 0 or plus or minus 1, these two things will not be equal to each other. And remember, homogeneity says that this should be equal to this for all scalars k. So that's what we're showing is not the case here. This is k times t of a. So this is not equal to this for every choice of k. Therefore, t is not linear. Okay. Here's another non-example. This one is going to take polynomials from P2, so polynomials of degree 2 or less, and map them into R2 vectors with two components. And we define this function this way. T of ax squared plus bx plus c is going to be equal to a minus b, that's the first coordinate or first component of this vector, and then a plus c plus 1 over here. Okay, so notice it's using the coefficients of the polynomial to determine what the first and second component of this vector is. Now, I can approach this in a similar way. I can try to show that additivity or homogeneity fail. But a better way to do this is to use that theorem that we just talked about over here. If t is linear, then these have to be true. And what's going to matter in this case is that the 0 vector of P2 has to be mapped to the 0 vector of R2. So if t is linear, that has to happen. But what does happen if I plug the 0 vector in to this function? Well, t of 0, remember that if we're thinking of that as a polynomial in P2, I could write that this way, 0x squared plus 0x plus 0, just so I can see what a, b, and c are. This would be equal to 0 minus 0. That's the a minus b that we are using here. 0 plus 1. This is 0, 1, which is not equal to the 0 vector in R, or in R2. So plugging in the 0 vector does not produce the 0 vector that it's supposed to produce if this is a linear transformation. Therefore, t is not linear. Again, we didn't have to use that approach. You could have tried to show that one of the defining properties of linear transformations doesn't actually hold, but this ends up making it a little easier, turns out. All right. This theorem down here, this is a really important one. It's going to matter in later sections as well. But basically what this theorem is going to say is that a linear transformation from a vector space V to a vector space W is completely determined by what that linear transformation does to a basis of V. So let me be more specific. If T is a linear transformation mapping V into W, and if we suppose that V is finite dimensional, meaning it has a finite basis, so let's let S be one such basis for V. V1, V2 through Vn. Then the image of any vector v in V, image meaning the output after plugging V into this function, into this transformation, can be expressed as in this form. T of V, remember V is any vector in V1, is equal to C1 T of V1 plus C2 T of V2 plus blah, 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 blah. So in other words, it's a linear combination of the images of these basis vectors. And not only that, the scalars C1 and C2 and all the way through Cn are the same scalars that we would use to represent V as a linear combination of just the basis vectors. Okay? So again, if you represent V as a linear combination of the vectors in this basis, then the image of V is a linear combination of the images of these vectors in S with the same scalars that we use here. And I'm not going to go through like a really formal proof of this because it's very easy to see why this is the case. If I want to evaluate t of v, I know that t of v can be represented this way, c1v1 plus c2v2 plus plus cnvn, because v is equal to this thing as a linear combination of those basis vectors. Now notice this is a sum of n vectors. If I use the additive property of linear transformations n times, I can break this thing up into a sum like this. This is just repeated uses of that additive property, right? Then each of these c's are scalars, so by my homogeneity property, they can all be brought out of each one, oops, c2, of those terms there, like this. That gives me that result right away. Okay, so that's a really important result, and I'm going to use the next example to sort of illustrate why. So we're going to let, in this case, we're going to be looking at a linear transformation that maps R3 into R2. But as is sometimes the case, we're not going to be given an explicit formula for this linear transformation. So I don't know what this linear transformation actually looks like. We're going to be considering the standard basis for R3, E1, E2, E3. Remember, this is a notation that we can use for the standard basis vectors. In R3, oftentimes we also call this I, J, and K. Remember, E1 is the vector 1, 0, 0. This is 0, 1, 0, and this is 0, 0, 1. So I don't know what this linear transformation looks like in terms of some kind of formula. All that I'm given in this is the image of these basis vectors under this transformation. I know that if I plug the first basis vector into t, the output is 3, negative 2. If I plug the second one into t, I get 0, 4, and the third one gives me 1, 1. I'm asked to find t of 1, negative 2, 5. How am I supposed to find this if I don't know what the formula looks like to plug this vector into? And the answer is to use that theorem. So first of all, notice that the vector that we're trying to plug in, our input vector, 1, negative 2, 5, is equal to 1 times 1, 0, 0, minus 2 times 0, 1, 0, plus 5 times 0, 0, 1, right? But these are the three standard basis vectors, which means I could write them as 1, E1, minus 2, E2, plus 5, E3, right? That's how I can represent that input vector. Now, if I want to plug this thing into the linear transformation t, negative 2, 5, that theorem that we just talked about says that whatever the scalars would be on the linear on the linear combination of these basis vectors, whatever those scalars are, 1, negative 2, and 5 in this case, can be multiplied to the images of those basis vectors. So this is minus 2 TE2 plus 5 TE3. And the problem gives us the value of each of these images. This is equal to 1 times 3, negative 2, minus 2 times 0, 4, plus 5 times 1, 1. What would this equal? 1 times 3 is 3, minus 0, plus 5, that would be 8. 1 times negative 2 is negative 2, minus 8, that's going to give me negative 10, plus 5, that'll give me negative 5. You notice we didn't need a formula. All we needed to know was what the image of the three basis vectors were, and I was able to find the image of this vector here, okay? These scalars only look like the coordinates of this vector because I used a standard basis. Your book does an example where you're also mapping R3 into R2, but with a different basis and a different input vector as well. And the scalars will look different in that case. So you do need to make sure that you have the correct representation of this vector as a linear combination with whatever basis you're given. Remember this example. This is really important for what comes later. after 8.1. All right. Now some more terminology. So let's let T be a linear transformation taking V into W, mapping V into W. And we're going to define a couple of very, very important sets associated with this linear transformation. This set, which, here's the notation, KER of T. This is called the kernel of T. See kernel here. The kernel is a subset of your domain. It's a set of vectors in V, things that act as inputs. And specifically, it's the set of all inputs, the set of all vectors in V, whose image is the 0 vector. This should be bold right here, and I can see that it's not, but that should be the 0 vector right there. Okay, so it's the set of all vectors in your domain whose image is 0. That's the kernel. Another really important set associated with this linear transformation is, instead of being a subset of V, it's a subset of W. We call it the range of T, and it's the same thing as what you think of as the range of a function. It's the set of all outputs, basically. Notice that the notation that I'm using here says it's the set of all W in W, such that T of V equals W for some V in V, meaning if I take all of the possible inputs in V, plug them into my function, and collect all of the outputs that I get from that process, then that makes up the range of T. Now, why is this important? Why do we make a distinction between R of T and the entire vector space W? Well, the vector space W may be larger than the range. Remember, we didn't call W the range before. We called it the codomain. An example is this function here, f that takes the real numbers into the real numbers, defined by f of x equals x squared. Okay? The codomain for this function, the way that I wrote it, is the set of all real numbers. But I know that the range of this function is not all real numbers, because this function doesn't have any negative numbers in its range. It only gives me non-negative numbers. So the range of this function is the set of all non-negative numbers, which is a subset of this codomain. That's why we're making a distinction here. R of T is the range. Okay, let's look at some important examples. So the zero transformation. Well, the kernel of the zero transformation is all of V, because think about what the zero transformation does. It maps vectors to 0, and the kernel is the set of all inputs, all vectors in V that get mapped to 0, so that would make it all of V. What is the range of T? Well, regardless of what this vector space W looks like, everything in V gets mapped to 0. It's the only output that we get from this linear transformation. The range is then 0. Identity operator, what about that one? Well, the identity operator maps vectors to themselves. So what would the kernel be? Well, if the output is 0, that must have meant that the input was 0, because, again, this function only takes vectors to themselves. No non-zero vector would be mapped to 0. That would be a different input from the output. The kernel of the identity operator is just 0. The range of the identity operator is all of V, because every input of V gets mapped to itself, which means every input or every output here is used up. Okay? Another example. This is an extremely important example because it ties in some stuff that we did in chapter 4. What if A is an m by n matrix, and we're defining the matrix transformation that we talked about at the beginning of this section, T of A, that maps Rn into Rm. Okay, well, if that's a matrix transformation, then the kernel of T, I should say T of A actually, and range of T of A, is the null space of the matrix A. R of T, the range, is the column space. So a direct connection between those two things. And to see why, what does the kernel of TA actually mean? Well, remember, we're looking for the set of all vectors x in Rn such that T of A equals 0. But this means that Ax would equal 0, because that's what this transformation does. The set of all, so in other words, the kernel of this linear transformation is the set of all solutions to this homogeneous linear system. But that is what the null space of A is defined to be. So the kernel of TA in this case is the null space of A. Similarly, if I'm looking for the range of this function, so for example, if I'm looking for the set of all y, in Rm such that there's an x in Rn that maps to y, that's the same thing. In fact, I'm not going to call this y, let me call it b, because that's going to be a more familiar notation. If b is a vector in Rm, and I want to find the set of all inputs from Rn that map to something in Rm, or sorry, let me back that up. The range would be the set of all b. Then we're looking for solutions to this linear system, right? But we proved back in chapter 4 that the solution set to this system of equations here, this matrix, this matrix equation, is exactly the set of all vectors that belong to the column space of A. We've already proven that. So that would imply that the range of T of A is the column space of A. All right, I'm gonna reference this again at the end, towards the end of this video, to tie together some terminology that we're gonna talk about. So let's do this. Let's talk about the kernel and range of some linear transformations. Let's let D be that derivative linear transformation that we talked about. This one taking continuously differentiable functions into functions, both of which are defined everywhere. What is the kernel? Well, the kernel would be the set of all constant functions, because if you think about it, we're looking for the set of all functions, d of f of x, which again, remember that's f prime of x, such that f prime of x is equal to 0. Well, in Calculus 1, you prove that this is only true if the original function was a constant function. So that would make the kernel the set of all constant functions. All right? We're not going to look for the range in this case. That's a little trickier. Just wanted to talk about kernel in this example. All right. Let's see. So, couple of theorems to wrap things up with, and some terminology that's going to tie some concepts together, like I said before. So for this theorem, let's again assume that T is a linear transformation mapping V into W. Really, really important. These two subsets of V and W that we've defined, the kernel of T, which is a subset of V, the range of T, which is a subset of W, turn out to be subspaces. They're actually vector spaces in their own right. Your book proves both A and B. Just to keep things from getting a little long here, I want to just prove A. The proof of B is not much different. You just use the defining property of the range, or what a range is defined to be. So remember, if you want to prove that a non-empty set is a subspace of a vector space, then you need to show that it satisfies the subspace test, right? The subspace test where we show that if U and V are vectors in this subset, then U plus V will belong to the subset, and K times U or K times V for any scalar K also belongs here. All right. So in order to prove this, first of all, and I neglected to state this in this proof, we do need to know that this is a non-empty set. But we know it's a non-empty set because according to a previous theorem that we already talked about, when you plug the 0 vector into your linear transformation, it always produces the 0 vector. So there is something in the kernel. We know that 0 does belong to this kernel. So now we say let U and V be any elements or any vectors in this kernel, and let's let K be any scalar. Let's start by showing that U plus V will belong to this set. I have to plug U plus V into my linear transformation. Because it's a linear transformation, I use my additive property to split that up. Now, because U and V both belong to my kernel, what that means is that T of U gives me 0, and T of V gives me 0 as well. So this is equal to 0 plus 0, which we know is the 0 vector. That's what we were hoping to prove, because that means U plus V gets mapped to 0, which makes U plus V an element of our kernel. Similarly, if I want to determine what happens if I plug KV into my linear transformation, from homogeneity, I can bring that K out. T of V, because V belongs to my kernel, is just 0, so this becomes K times 0, which again is just the 0 vector. That means KV is in our kernel as well. So by the subspace test, the kernel has to be a subspace of V. All right. Now, because we've established that the kernel is a subspace of V, and we didn't prove this, but you can look in your book, the proof is there. The range of T is a subspace of W. These two sets are vector spaces. That's what subspaces are. Subsets of a larger vector space that happen to be vector spaces in their own right. So that would mean that each of these, if V and W are finite dimensional, then each of these is going to have a finite dimension as well. So those dimensions are given a name, and these are going to be very familiar. The dimension of the kernel of T is called the nullity of T, and the dimension of the range of T is called the rank of T. We've seen those terms before. Remember, when we talk about a matrix, the nullity is defined to be the dimension of the null space of that matrix. And R of T is defined to be the dimension of the, rank is defined to be the dimension of the row space or column space. Remember, they turn out to be the same. Well, we showed over here that in the case of a matrix transformation, the kernel of T is the null space of A, the kernel of T of A. So these dimensions would have to match as well. And same thing here. The range of T of A is the same as the column space of A, so these would have the same dimensions as well. Now, if you remember, I had said earlier that something we're going to show a little bit later down the road is that all linear transformations, regardless of what these vector spaces are, can be thought of, as long as they're finite dimensional, can be thought of as matrix transformations. And because all these linear transformations have a kernel and a range, but those can be associated with a null space and a column space, it makes sense that we would reuse these terms, nullity and rank, to talk about the dimensions of the kernel and range independently. So that's important. We'll find the rank of a linear transformation in an example in a minute. But first I want to talk about this theorem. We're not going to prove this theorem. Your book gives the proof as an optional proof. And we're skipping it here because we've proven this theorem in the matrix version back in chapter 4. And the ideas that go into that proof are not much different than the ones that go into this proof. But I encourage you to take a look in your book and maybe read through that proof, see if you understand it. If T is a linear transformation from V into W, and if V is finite dimensional, then the range of T will also be finite dimensional. Even if W is not, the range of T will still be finite dimensional. And the rank of T plus the nullity of T is equal to the dimension of V. This is the rank nullity theorem, or the dimension theorem, that we talked about back in chapter 4. And remember, if this T is the matrix transformation TA, then this rank is the dimension of the column space of A. This nullity would be the dimension of the null space of A, and the dimension of V would be the number of columns in A. So this reduces to that case that we talked about already. Okay, very, very important theorem. Let's do one example where we use that theorem, and then that's going to be it for section 8.1. So D is going to be the linear transformation that takes polynomials from Pn, maps them into other polynomials from Pn, so it's an operator. And it's going to be that derivative operator, just restricted to the polynomials in this case. I want to find the rank of T. Well, rather than try to find the rank of T explicitly, what I'm going to do is use the fact that I know what the dimension of V already is. I know that the dimension of Pn is n plus 1, and see if I could find the nullity of this transformation, see if that's easier. Well, we've found the kernel of this transformation previously. We already did this right here. We showed that the kernel, and even though these functions are not just polynomials, the kernel would be the same because it's still a derivative that we're talking about. The kernel is a set of all constant functions. Okay, so the kernel is the set, kernel of, we're calling this D, kernel of D is the set of all constant functions in P naught, or Pn, such that C is a constant. Okay? Well, if I want to know what the dimension of this is, notice that the set of all constant functions can be written as C times 1, where 1 is a vector in Pn. It's a polynomial of degree 0. It would belong here. So this entire set is the span of this one vector. This one vector can be thought of as the basis for the kernel, which implies that the dimension of the kernel, or the nullity of D, is equal to 1. Its basis only has one vector. So according to this, the nullity of D is 1. The dimension of Pn is n plus 1, and I get this. Rank of T is equal to, plus the nullity, which is 1, is equal to n plus 1, which implies that the rank of this derivative operator, that's supposed to be a D, is equal to n. Okay? I didn't need to find the rank explicitly by finding the range. I could use this theorem instead. That's going to be it for 8.1.